Hello and welcome. Today we're going to be talking about creating power series from other power series. So I'm going to really be talking about two different problems. I'm going to start with this one. F of x is equal to the integral of e to the negative x squared dx with the additional fact that f of 0 is equal to 0. Okay. This function is actually important in statistics and probability. And we also note that e to the negative x squared has no simple antiderivative. And what I mean by simple is that we can't just write down it as a closed form expression. No closed form expression of what I will call elementary functions. Okay. With that said, we want to know then, how do we compute the antiderivative of e to the negative x squared dx without having an antiderivative? So I want to know that question. Okay, well the answer is, we're going to use series. Okay, so we're going to use power series. All right, so that's our goal here, is to find our power series of f of x. And we're going to do it, and the whole point is we're going to create power series from other power series. We're going to use our fact that we know that e to the x is equal to the sum of n equals 0 all the way up to forever of x to the n over n factorial. Okay, so the idea here is the following. First, we're going to see if we can. We're gonna basically express e to the negative x squared as a power series, and then 2, integrate. Integrate number 1 to get f of x. All right, so let's start this. The idea here is if I have e to the negative x squared, I can write that as e to the negative x squared. So all I did was put a parenthesis there, but you'll see it actually really is helpful, because now when I write down the series, n equals 0 up to forever, and now I'm going to put my parenthesis there, and now what I'm going to put inside of here is negative x squared. All right, so that's nice. That helps us. So now we have a way of representing this. I'm going to do a little bit more work here. Do a little bit more simplification. And factor out the 1. And then have an x to the 2n there, all over n factorial. And the idea here is as follows, right? If you have x to the negative x squared to the n power, whatever n is, I can write that as like this, and then use the power of exponents, that an exponent of an exponent is going to be the product of the exponents. That's what the power will be. All right, so this right here, to summarize then, so far, this is the power series for e to the negative x squared. So now what we're going to do is integrate. So it's okay to integrate term by term. So integrate term by term. So what we're going to do is I'm going to integrate. Back up here for a second. We know that f of x is equal to the integral of e to the negative x squared dx. Okay, and that's going to be equal. And here's the important point about equal signs. Wherever I see one of those, I can put one of these boxed expressions in its place, so I'll do that. All over n factorial, just like that. And then I'm going to integrate by dx. Okay, so what I'm going to do is, of course, the integration passes through sums. And it passes right through constants. Okay, and then we have the integral just right here. Like that. Okay, and this summation then says that basically we're going to be doing infinitely many integrals. Each one is this x to the power 2n, for n ranging all the way from 0 up to forever. Well, we can do that real quick. This is going to be the sum of n goes to 0 up to forever. We have a negative 1 to the n power all over x to the 2n plus 1 all over n factorial times, and we're doing the reverse power rule, so this is going to be a 2n plus 1. All right, so there we go. That is it. That is the answer to our finding a power series. This right here is equal to my f of x power series. And that is really nice. So now, of course, f of x, I said that was important for statistics. You can use a computer to estimate the series very simply. And that will work really well for you guys. Okay, so that was our first problem, and I hope that, and this was an example of integrating to get our power series. Okay, so in this next example, what I'm going to do is we're going to actually do an example involving differentiating. To get our power series. Okay, so we'll start with this example now. I'm going to start again with a capital F of x. This is the function we want to find, and it's going to be equal to 1 over x plus 1 quantity squared. Okay, that's my capital F of x, and I want to find out what's the power series that needs to go here in order to solve the problem. Okay, so what we're going to do is, so the hint is we're going to use this power series, the geometric. So I'm going to write that down, and I'm going to give it a name. I'm going to call it g of x for geometric. It's 1 over 1 minus x, and it's equal to, I'm sure any student of sequences and series knows this one, probably by heart, x to the n, with the proviso that x has to be less than 1 in absolute value. All right, so what we know, and then I'm going to give another hint, and so on an exam problem, I would probably give you all of these hints, is to note that if I were to take the derivative of g of x, this would be 1 minus x 1 over 1 minus x quantity squared. Okay, and so this is, this is similar to capital F of x, but there's some differences. So I'm going to put a question mark there. But note that what I'm going to do is now, so that would be the hint I would give you guys. Okay, so note. So here's the answer. What we have to do is do a little bit of rearranging of things. Note that if I go g of negative x, well, that's going to be 1 over 1 minus a minus x, right? Which is equal to 1 over 1 plus x, like that. Okay. All right. Now if I take, let's call this something else. I'm going to call this h of x, right? So if I take the derivative of h with respect to x, of course I'm going to get, there'll be a negative there. Quantity squared, negative 1 over 1 plus x quantity squared. And that, of course, is equal to negative capital F. All right. So it seems like we've got this. I think we can figure this one out. All we have to do now is put all these things together. All right. So what I'm going to do is I'm going to start with that. G of negative x is equal to 1 over 1 plus x, which is going to be equal to the sum of n starting from 0, going up forever. And now what I'm going to do is I'm going to put negative x inside of there to the n power. Okay? And that simply utilizes our geometric series that we know, but we're plugging in negative x instead of just x here. Right? And I can do a little work here and factor out that negative 1 like that. And that just simplifies my problem a bit. Helps me out in terms of what I'm going to do next. All right, so now I know that this right here, I call this h of x, right? So now what I'm going to do is I want to get to here. I want to get to capital F, and I know that I have to take the derivative of h. So what I'm going to do is take the derivative of this sum, okay, and that is going to be the derivative. The derivative will pass through the sum, and it will zero in, of course, on anything that has an x in it. Any constant, in this case negative 1 to the n, those are just constants, so the derivative will pass right through there. That's the classic rule of derivatives. All right, and now we're going to take all those derivatives for every single n value. All we're doing is taking infinitely many derivatives, but we're using our summation notation to kind of help us with the bookkeeping, so we could do it all at once. Okay, of course that's going to end up with the power rule like that. All right, now this was equal to negative capital F of x, right? So what I need to do is, of course, find f of x, which is just going to be the negative of the sum, n equals 0, going up forever, of negative 1 to the n times n, x to the n minus 1. So that's an okay answer. But let's simplify. We should simplify. All right, what I really want to do is I want to re-index the sum. And what I mean by that is that this is really kind of clunky, right? So remember, capital F of x, this is equal to 1 over 1 plus x quantity squared, just like we had done before. But what I'm going to do is I want to actually see if I can just take this sum here and do a little work here. So first off, you see that there's a negative 1 in the front of that. So I'm actually going to distribute that inside to everything. So that's actually going to give me a negative 1. Now, rather than having n of them, I'm going to have n plus 1 of them, multiply by n, and then n, x to the n minus 1. Right, and now what I want to do is actually just see if I can work out what all of these are. See if I can find the pattern. So I'm going to start with n equals 0. And you notice here that because there's a coefficient of n, the first term is just 0. So in fact, I don't even need to start my sum at n equals 0 as it's written right now. So what I can write right here is actually or n equals 1. That would be fine as well. The next time, now when I put in n equals 1, right, so there's the n equals 0, and now I'm going to do the n is equal to 1 term. So of course, this is just going to be x to the 0, all right, so that's just going to be equal to 1. And now I'm going to go plus, and now we're going to do the n equals 2. And we see here, now I finally get a negative 1 coming out of it, because that's going to be a negative value there. And we're going to multiply by 2. And then we're going to have, of course, an x to the first power. So that's that term. And now we're going to go n equals 3. I'll do one more here just to kind of solidify that this is going to be a 3 times x to the 2 power. So what I'm going to reindex, so n is going to go to n plus 1. Okay. Oh, I'm sorry. I need to back that up. Really, it should go to n minus 1, right? Because that really should be 0. And I'd like to make that 1. And I'd like to make this 2. Because I really want to do it with the powers of x there. So what I'm going to write now is this. What I want to note, though, I'm going to put a little asterisk here. Note that basically even powers are positive. Okay. So that should help us set this thing up. So there's my sum, n equals, and now I'm going to start at 0 again, just like I described right there. Okay. I'm going to go up forever. We're going to add all these up. And the first thing I'm going to do is have we know that even powers are positive, and that includes n equals 0. Okay. And so what I can do is write negative 1 to the, now if I want even powers to be 0, what I can do is just put n there like that. And now I'm going to have do you notice here that for the n equals 1 term, the first power x, I have a 2 there. So what I need is an n plus 1 right there. And then I have an x to the n right there. Okay, so that is, I think, is just slightly cleaner. This is a bit nicer a representation. And that just makes things simpler in terms of how we index things. And I think re-indexing is a really important skill. I think if you're going to program anything on a computer, you need to be able to index things. And if the index isn't working very well, you need to be able to re-index things to make it better. All right, I hope you enjoyed this representation of power series video. We covered 2 different cases, differentiating and integrating, and shows why we might want to do these things. All right, thanks very much.